saying anything. And the short answer is no, I don't really know anything more than what you heard. So we don't know what the event was that hit Hitomi or caused Hitomi to move out of orbit. I'm sure you've seen Jonathan's emails and notes that have shown that the orbit has changed. It appears to be tumbling. We don't know why. They have had what I'm interpreting as being basically carrier contacts from it. So has been cleared up. It didn't break into pieces. A couple of bits of mylar or something came off of it that were seen by radar, but they're small. So there is still a satellite. There is still got. It still is able to communicate how. Obviously, the immediate questions are how much power is it getting, how much power is it drawing, what can they do to recover it. All of these are questions that there's a small group of people who have been working on this for a decade or so, probably know the answers to, or are working on knowing the answers to. And until they know something, they're not going to be talking to anybody else. JAX is taking this about as seriously as it's possible to do so. The equivalent of the NASA administrator is heading up the board that's reviewing this. So, obviously he's not going to be able to do very much, but trust me, if he makes somebody a phone call and says, we'd like to borrow your downlink center, he will get an answer. So they're doing everything that's humanly possible. My personal favorite was apparently the Minister of Science instructed JAXA to take every effort in order to recover the spacecraft, which I'm sure was news to JAXA. So that's it. All hope is not lost. It's certainly not a situation that anybody wanted to be in. And I think the recovery is going to take a while. If it's possible to get back into communication, and if it's possible to stop it from tumbling, it's still going to be months before they get back full control and figure out what's going on. So originally we've been talking about having an AO in the summer. That's certainly going to be delayed if it happens. So that's it.
The main event this afternoon is going to be Sebastian Heinz, and he's going to orient the title of his talk. I'd like to say a few words about him before we actually see him the floor. He did his PhD in Colorado. He then did a postdoc at Max Planck Institute for Astrophysics, and then he came back to MIT. And after MIT, he then went to the University of Wisconsin, where he's now an associate professor. Full professor. Oh, your website is out of date.
It is.
Okay.
Our website's always out of date.
His main focus for the past some number of years has been on observables of black holes and their effects on environments, growth and evolution of cosmic structure, numerical simulations, and it's these numerical simulations that I think of him in best. He has a wonderful paper on the pioneering paper on the fundamental plane of black hole activity with Maloney and DiMatteo. And just coming back to his simulations, he seems to have this magical ability to really almost put himself inside his simulations. He can put himself on one of his little clumps of gas that's moving around, and he can just, when he talks to you, he can just tell you. He actually can understand and feel the physics of how these things move around. And so when you finish talking to him, you truly have really a new insight, new understanding of how the simulations behave. And he really focuses on, he simulates and really focuses on the key areas of the physics in the simulation. Anyway, it's a delight to welcome him as he is now going to be the 7th Stephen Murray Distinguished Lecturer. And so we're very excited to have him here. The title of his talk, even though he's mostly known for his studies of black holes, he's going to talk about In the Ring with Circinus X-1, a multi-round fight to understand a stubbornly unusual X-ray binary. Sebastian, tell us all about it.
Thank you. Well, thanks for the wonderful introduction, Bill. It's great to be back and to see so many familiar and so many new faces. So, as Bill said, I will talk to you about a neutron star X-ray binary today, not about black holes and not about feedback at all. So some of you might be surprised. I was surprised when I started working on this. There's a lot of serendipity involved in this, and so it's always good to take advantage when that arises. So before I start, here's my list of collaborators out of date. Mostly this is Mike Burton and Paul Sell, my former grad student who's was at Texas Tech and is actually moving to Crete. So let's launch right in. Here's my outline. I'll briefly review the flavors of neutron star XRB binaries. There are two. And then I'll ask the question, Circinus X-1, which is it? The resounding answer is yes. And in the second half, I'll talk about bat astronomy, so light echoes and what they can tell us about XRB binaries. So when a massive star dies, this is the very simple picture. We get a supernova and a neutron star. Right, so this is the neutron star, the supernova remnant on large scales. There should be a credit. Well, I guess the caption is not appearing. Well, this is a wonderful Chandra image, and you've all seen this many times. It's on many hallways in this building. And so I will talk about both of these things today. So most stars are born as binaries. And so if the massive star in a binary explodes, the supernova can sometimes disrupt the orbit of the binary system, and sometimes the companion star can hold on to the compact object that's formed in the supernova. And if that's the case, somewhere in the evolutionary state of the object, you can transfer mass from the companion star to the compact object. And so you can have a neutron star or a black hole as the compact object, and if you transfer mass from the companion either by Roche-lobe overflow or by wind-fed accretion, then the accretion flow is very X-ray bright, and you made an X-ray binary. So I'll talk about that today. And so focusing now on neutron star X-ray binaries, we distinguish them based on their phenomenology, and that's mostly driven by the field strength of the neutron star. So if you have a high field neutron star, then accretion, here sort of indicated by this accretion disk, will within the magnetosphere of the neutron star be funneled onto the poles, the magnetic poles of the neutron star. And if the magnetic axis and the spin axis of the neutron star are misaligned, then you get an X-ray pulsar. And the accretion rate, because the accretion flow is funneled onto the poles, is sufficiently high, the pressures and temperatures sufficiently high that you get steady nuclear burning on the polar cap. You don't collect any material that you can burn later on. So here's an example of an X-ray pulsar. You see the very nice periodic pulsar signal of this particular example, and you can sort of see the artist's rendition of the magnetosphere clearing out the disk well away from the surface of the neutron star. So that determines the phenomenology of this source. On the other hand, if you have a low-field neutron star, you can have regular accretion all the way in basically to the surface of a neutron star, and there's no real magnetosphere. And so then the accretion is basically spread over the surface of the neutron star. The accretion rate locally is lower per unit surface area, and you do not get steady burning where the accretion stream hits the neutron star. And instead, you accumulate fissile material, nuclear material to fuse in unsteady nuclear flashes. And so you get type 1 extra bursts from these low-field sources, which is the number one indicator that you're actually looking at a neutron star. So you need to have a surface in order to collect material on it that you can then burn in flashes. So here's an example of type 1 extra bursts from my favorite source, Circinus X-1, and I'll spend the rest of the talk talking about that particular source. So these are not pulsations. These are type 1 extra bursts. So we now know, based on two detections of type 1 extra bursts in 2010 and 1986, that this is a neutron star system. For a while, there was some doubt about this because the original detection of bursts was done by Exosat with a very large field of view. You can never be sure that the source that did the burst was actually Circinus X-1, but this is a swift observation, and it's very clear that only Circinus X-1 was in the field of view. So the canonical picture is then that we have weakly magnetized neutron stars that have type 1 X-ray bursts, and we associate those, they're found in low mass X-ray binaries, and we associate those with low field objects. And because they're in low mass X-ray binaries, and because neutron stars are generally believed to be born with high fields of the order of 10 to the 12 Gauss, we assume that these are old neutron stars. So old neutron stars are weakly magnetized. We find them in low mass X-ray binaries, and we see them having type 1 X-ray bursts. They also have jets. They have QPOs. Young neutron stars are generally strongly magnetized with fields of the order of 10 to the 12 Gauss or larger. We find them in high mass X-ray binaries, and they tend to be X-ray pulsars. And so the conclusion would be then that the evolutionary timescale for the magnetic field in neutron stars is much longer than the evolutionary timescale of high mass stars. and then that you find low-field objects only in environments and in X-ray binaries where the magnetic field in the neutron star had time to decay to the level where you actually observe type 1 X-ray bursts, which is something like 10 to the 9 Gauss. So Circinus X-1, the reason I started studying Circinus X-1 is that it has a beautiful radio jet, and it is one of only 2 galactic X-ray binaries that have a radio nebula around it. And so we used to call this the radio lobe of Circinus X-1, and I study jets and radio lobes, and I wanted to understand why this is basically, this and SS433 are the only sources in the galaxy that show large-scale diffuse radio emission. So I wanted to look at Chandra images of the source and study the radio nebula. So here are the vital statistics of Circinus X-1. It's in a 16.5-day orbit with pretty high eccentricity. This is an estimate based on infrared detections of what seems to be the companion. It shows X-ray dips. And one of its most interesting features is that the orbital evolution time is very, very short. So if you divide the orbital period, p, by its time derivative, it's of the order of a few thousand years. So the orbit evolves rapidly, and it's shrinking. So that's very surprising, because we know that it has type 1 X-ray bursts. It doesn't have any pulsations. It has jets, and so it must be a low-field neutron star. And low-field neutron stars are old. And they're low-mass X-ray binaries. If the orbit evolves on a very short timescale, that's a contradiction, right? We have a paradox on our hands. So the companion was claimed to be an A-B-type supergiant, so it would be a high-mass X-ray binary, if that's the case. Although there were some other recent claims that it may be a cool companion star. It's highly extincted. It's right in the disk of the galaxy, with a column of about 2 by 10 to the 22 per square centimeter. And so the distance was not known accurately to this object, somewhere between 5 and 15 kiloparsecs. It's in the disk of the galaxy. Distance measurements were sometimes based on the column or some based on the type 1 X-ray bursts. Okay, so we have a contradiction. The question is, which is it? Is it young? Is it old? So the first look I had at this object was in archival HETG observations. And I showed you this image the last time I stood here and gave a talk. And only X-ray astronomers, and there are lots of those in the audience, will appreciate this, right? So you clearly see this jet over here, right? Lots of photons, right? You can count them. You need at least 2 hands to count them, so that's a good detection. Obviously, this is a gratings observation, with the 2 dispersed spectra and the read streak. So this is not the jet, and this is not the jet. This is the jet. So you have to sort of massage the data a little bit and see that there is at least a 6 to 7 sigma significant excess where the red is over here. And the blue is the radio jet overlaid. At least it's aligned with the radio jet. Right? Now, you don't have to believe me on this, because we did get more time on this. And so we observed this source. Let's see, this observation was done somewhere here. And this is the long-term light curve of this object. Right? So in the 1990s, it was rather bright. So it was, I think, 1.3 crabs for a very long time. And then it went on to sort of a secular decline over a decade. And now we're actually over here. And this is 2015, so we're here. Okay. We observed it again, now without the gratings and when it was really, really dim. Why do we want to observe it when it's really dim? Well, we're looking for diffuse faint emission near a bright X-ray binary. And so you don't want to look when the X-ray binary is bright. You don't want to look for the corona when the sun is bright. You want to look during an eclipse, or you want to look when you want to look for Mercury when the sun is below the horizon. So, so that's what we tried to do. Now there's no coronagraph that we could use, so we had to wait for the object to become really dim. So here is the follow-up observation, and you see, so the color scale here is the X-rays, and the green is a new higher resolution radio image of the source, and you can see that there is a very clear jet that we detected in X-rays, and it's really nicely co-spatial with the radio image of the jet. Okay, and if you take a spectrum of the X-rays and the radio, the X-ray jet is perfect power law emission, and it has a spectral break of 1/2 relative to the radio, which is exactly what you expect from synchrotron cooling. So we can use that to put an age on the plasma that we see in this shock over here. We interpret this as a shock. And the age is about 1,500 years plus or minus factor of 2. So there is a structure of order of parsec in scale inside the radio nebula of Circinus X-1 that's being powered by some outflow from the source that is a few thousand years old. Okay. So here is another image of the same observation, now smooth, heavily, because we want to look even further than the obvious jet emission that we found in this image. So here's the neutron star. Here are the two shocks that we saw. And then you see that there's this red glow on even larger scales, and of course, a couple of background point sources. So the question is, what is this glow? And whenever I show this to any collaborators, I always said, oh, this is dust scattering. It's a dust scattering halo. It's great. But it's not interesting for the X-ray binary. And so we sort of ignored it for a little while, but it sort of kept bothering us. And so first, we can easily rule out that this is the PSF. It's on much too large scales. It's very soft. So it's not the PSF. Is it dust scattering? And so usually I don't show the slide, but in this audience I feel I could, because there are enough experts to appreciate this. So this is an observation that was done, I think, in 2000 of Circinus X-1 when it was really bright. Remember, the source was above a crab, and so this was an extremely bright source, and there was a great observation. You can see the bright gratings dispersed spectra here. They saw lots of interesting lines, P Cygni profiles and such. And you also note how careful the observers were to put a telemetry window in there so they don't saturate telemetry of this really bright source. And you also note how very carefully the source was placed outside of that window so that we could do the study that we needed to do later on, a decade later. So here's the dust scattering halo. Here is the slightly overexposed source. Right? I don't think anybody would be allowed to do that on purpose. Belinda is shaking her head. So you try to avoid this kind of thing usually. So we were lucky that this observation was in the archive, and we can just calibrate the brightness of the dust scattering halo relative to the brightness of the source, and we can rule out that the diffuse emission that we found around the source is dust scattering. So here is that nebula that we found, the diffuse nebula. Here are the two jets and the neutron star. So this image is stretched to show the nebula. It's actually rather uniform in brightness, and then it has a very sharp edge to it. And remember I said that this is a radio, the source has a radio nebula. So the observations that existed when we took this Chandra image were pretty low resolution. This is a southern source. VLA cannot see it. Also note that this is where the chip cuts off, so we don't have any information below here, which is unfortunate, as you'll see in just a second, because when we look at the radio image, this is the radio image of the same object. This is a compact array image at much higher resolution. You notice that this funny extension that the radio lobe has to the south is exactly below the chip cutoff. So we can't tell you anything about that, but hopefully in the future we will. Fingers crossed that the object behaves. So here is that radio nebula, and you see the very sharp edge on this nebula, and it's sort of edge brightened, right? So it's interesting. It's very different from the very low resolution image that people had taken of this object. So let's compare the radio and the X-ray. So on the left, there's an overlay. The radio is now heavily binned. The X-ray is heavily binned. So the red, yellow color scale is the X-ray nebula, and then the sort of cyan image is the radio, and they're perfectly co-spatial, right? They overlap exactly. Here are the contours of the X-ray in white and the radio in red, and there's a very, very good match in the two nebulae. And then there's this extension that we don't really know what it is. And it's much larger than the scale of the jet, of course. And so the question is, what is it? So we took a spectrum, right? Of course, you get a spectrum for free when you do a Chandra observation with ACIS. So this is the spectrum of the nebula, and it's very clearly not a non-thermal spectrum. Or rather, it is a thermal spectrum, a non-equilibrium. So that was a double negative, right? You don't want to do that. So it's a thermal spectrum. It's not non-thermal. It means it's not synchrotron emission. It's thermal, and it's also non-equilibrium. And so here are classic magnesium silicon sulfur lines of a shock spectrum. So it's a blast wave. And so what kind of blast wave do you see on those kinds of scales? We interpret this as a supernova remnant of the source that gave rise to the birth of the neutron star. So why is this interesting? Well, let's go through the numbers. This is not really showing up very well here. Okay, so here are the spectral constraints on the properties of that nebula, of the supernova remnant. Age in 1,000 years, 1, 2, and 3 sigma contours, and then the energy in the blast wave. And you notice that the contours are really poorly constrained to the upper left here. That's because we don't have a good handle on the upper shock temperature in the plasma. You can't really measure that well because the only constraint you really get from the spectral analysis of these kinds of thermal spectra is the low end of the temperature range for the electrons because they cool. And so we have a good upper limit on the age, which is derived from the lower limit of the electron temperature. And so there's a pretty wide open swath, but we know very certainly, I guess, with very high certainty, 3 sigma upper limit on the age is less than 5,000 years, with a small dependence on the distance to the source, right, in units of 8 kiloparsecs. So this d8 is the distance to the source in units of 8 kiloparsecs, right? So that we'll come back to in just a little bit, and it would be nice to know that distance accurately. So here are the constraints on the remnant, and it's consistent with typical supernova remnants. Now, could it be that we're just looking at a jet-inflated shock wave? This is highly unlikely. It would have to be 5 orders of magnitude out of equipartition. It's 5 orders of magnitude too faint in the radio to explain the energy you need to drive this nebula. And it would require more than 100 times Eddington constant supply of energy from the source to explain this. And so the radio nebula, therefore, is not inflated by the jets. It's not actually a radiolobe. It's actually just the supernova remnant, which is interesting because, remember SS433, the other galactic X-ray binary with the radiolobe is also a supernova remnant, W50. And so it's actually rather similar to that source. The age of the entire nebula is consistent with the age of these inner shock waves that we detected for the synchrotron jet. And so we interpret the caps in here as the location where the jet impacts something heavy and large and maybe dense, so probably the reverse shock. Okay, so the best fit age is something like between 2,000 and 3,000 years, and at that age, Circinus X-1 is by far the youngest X-ray binary, not the youngest supernova remnant, but the youngest X-ray binary that we know. So there are only 3 other X-ray binaries within remnants. One is SS433, one is a pulsar in the LMC, and then there's another object in the SMC. And all of those are older than Circinus. And so this makes it a great object to study the evolution of X-ray binaries. So the companion must be a young star, because the high-mass star that exploded to give rise to the neutron star that we see today must have formed at the same time as the companion. And so this supports the idea that it's an A or B type supergiant companion that's also a massive star. But as I said, there was a recent paper that claimed that perhaps the star is just a blast-heated young star where the energy of the supernova affected the photosphere of the star sufficiently to make it look like that. An interesting possible alternative that we find rather unlikely, but it would be extremely interesting if it were true, is that the neutron star was produced in an accretion-induced collapse of a white dwarf. In that case, the system could be older, and nobody has ever observed any accretion-induced collapses, so that might explain why the neutron star is so different from typical young neutron stars. But we find this pretty unlikely just because of the rapid orbital evolution, and accretion-induced collapses don't really change the orbit very much of the system because there isn't much mass that's liberated when you do this. And so the orbit would have had to evolve even before the accretion-induced collapse, and that would sort of go against the idea that the system is old. Okay. So as I said, this object is known to be really young because we observe the orbit of the binary to change over a few thousand years time scale. So that's consistent with the age that we derive from the blast wave. And it's also interesting because if you have such a young system that's still evolving rapidly, it means it's out of equilibrium, right? So the neutron star basically just formed yesterday in cosmic times. And when you have a supernova explosion and you change the orbit of the system, it's very likely that all the 3 angular momentum vectors in the system are misaligned. So the neutron star is spinning this way, the companion is spinning that way, and the orbit is yet spinning in a different way. And so you have three angular momenta that will precess around each other. And so that might easily explain why you have these very large swings in accretion rate that change over decade periods, and also the very rapid flares that we see from time to time from this object, just because the orientation of the equatorial plane of the companion star changes with respect to the orbit. And sometimes when you come close by, you can rip more matter off. It's consistent with predictions for post-supernova orbits for X-ray binaries. So this is an old paper by Neil Brandt and Phil Pozitlovsky from '94, where they predicted where objects of this kind would be found in the period and eccentricity plane. And so this would be Circinus X-1, and it's right in the center of where you would expect an orbit like that to be. So that's nice confirmation, and it also tells us that we can actually study the evolution of this orbit in response to accretion. We can measure the accretion rate from the X-rays. We can actually see how the orbit changes in response to that. So it's a great system to study all sorts of orbital evolution. And finally, and maybe most interestingly, because we know the object has type 1 X-ray burst, we know that the field must be low, much below the typical birth field of neutron stars of about 10 to the 12th Gauss, something like 10 to the 9 Gauss. So that's 3 to 4 orders of magnitude below the typical field of young neutron stars. And so this is interesting because if it were an isolated neutron star, we wouldn't see it as a pulsar. And the question then is, why was it born with such a low field? And maybe there are other objects, we just don't know about them. Why was it born with such a low field? Was it either born inherently with this field, or was the field suppressed by fallback accretion or by near-Eddington accretion? It's very hard to suppress the field by ongoing accretion in such an object. So I'm not going to go into the details, but we know that there are near-Eddington X-ray pulsars that are still pulsars. So it certainly does not work for all near-Eddington sources. And the other thing is, of course, that currently the accretion rate is well below Eddington on average. And the buoyancy time for magnetic fields in neutron stars is very short. And so we should be seeing the field currently because it's just not accreting rapidly enough to keep the field buried. Okay. So this is a great change to our interpretation of this object. As I said, we would like to know the distance. And so, let me see, what time is it? Do we have a clock? 1. Okay. So we have enough time to go into the details here a little bit. So we thought, well, this is a great object. We want to study it more. We asked for Chandra time, and we got it. And so here is the observation that we did of the object in 2014. And you obviously notice that this is an interesting observation. Here is the neutron star in a jet, and then here is the the supernova remnant, right? And then here, and here, and here are very bright rings of X-ray emission. And so you might ask yourself, what are these rings, and what can we learn from them? So I know that some of you know the answer, but those of you who don't know the answer, any guesses? So what's that? Winds. That would be interesting. So I've actually, several people suggested that maybe this is just some pulsation or some shocks that were driven out into the interstellar medium near the source. But that turns out to be not the case in this object. So let me show you the X-ray sky just before the observation. Okay, so this is the MAXI all-sky movie that you can make by just copying every single day's observation of MAXI onto your hard drive and then making them all into a movie. So here's Circinus X-1 in that white circle, and you notice on, was that March, is that 20 or 26? It doesn't really matter. In 2013, Circinus X-1 was not detectable by MAXI. And so let's turn on the movie and keep your eyes on Circinus, right? So this is the X-ray sky. And nothing much is happening, so we're now in August of 2013. Just September, and then now keep your eyes on Circinus. Now notice that it's flickering, and now it's really bright. And so all of a sudden it becomes the third brightest X-ray source in the sky, and then it turned off again. So this is the date of the observation, and about a month and a half before, Circinus X-1 had a huge flare. So here's the light curve of Circinus X-1 from MAXI. And here is the first Chandra observation that I showed you before. So it was nice and quiet, perfect for observing it to see diffuse emission. right? Because we don't want to see the neutron star, we want to see everything around it. And then here's that flare. So there was a first blip, and then a very bright flare that followed. And it's about 40 days before the first observation. And then we had another second Chandra observation, and then 3 XMM pointings. Okay, so it's dust scattering. These are dust scattering rings as an echo from that flare. And how does that work? So here's the geometry of dust scattering. Suppose this is Circinus X-1, it's our beloved neutron star. Here's the observer, and the neutron star is a distance d, and it emits a flare. Okay, so here's our flare, right? That's a flare photon, and we'll follow 2 photons. This is the flare, and we'll follow that photon directly to the observer, right? So we see that flickering. Those are the photons that you saw in the Maxi movie. And then we'll also have a photon that goes off in a different direction. I mean, there are photons going in all 4 pi directions. We don't know if the flare was isotropic or not, but let's assume it was mostly isotropic, so there are photons going in every direction. We'll just pick this particular one, and then we'll have this photon interact with a dust cloud somewhere between us and the source at some fractional distance x times the distance to the source. Right? So that's the fractional distance x. And so these 2 photons will travel along their way, and so the first thing that happens in this cartoon here is that that second photon will hit the dust cloud. What happens when X-ray photons interact with dust? Often nothing, but if there's enough dust, the photons can get absorbed and they can get scattered. So this photon will get scattered, and we just pick this particular photon because it will get scattered back to the observer. Right? Other photons will get scattered in other directions. And just before anybody complains, this sketch is not to scale, right? So this distance compared to this distance is tiny, right? So we're talking in arc-minute angles. So it would be like this, right? Okay, so just to demonstrate, I stretched this out. So this photon gets scattered, and it will be emitted, scattered back to the observer. The next thing that happens is that the flare photons get received, right? We see them with Maxi, and we see the flare in the sky. But the scatter photon is still a little bit behind because it had to travel a longer path. And then the next thing that will happen is that that photon appears with some time delay, and it comes from this direction. So we actually see the photon coming from over here, not from the source. And this isn't the only photon. Other photons get scattered as well, and so what we see is a ring. And the size of that ring depends on the time delay. So here is another sketch, same dust cloud. Now we have 3 photons. Right? As I said, they're isotropic, so let's pick some other random photon. Right? So these are the photons we already discussed, and then this is a third photon which gets scattered, which gets emitted in a different direction. So the first photon gets scattered, the second photon gets scattered. I pick 2 photons that get scattered back to the observer, right? And so we see the flare. We see the first photon coming from this direction. And sometime later, the second photon that was scattered at a larger distance with a longer time delay and a larger angle will be seen at a larger distance from the source. So what we would expect for an echo is that the size of that ring is increasing with time. And we can check that. So this is the prediction, right? So an echo must produce rings with increasing size and radius. And the size of the ring should increase with the square root of the time. And so here are the 2 Chandra observations, and I've conveniently overlaid these rings to guide your eye as to where the rings actually are on the X-ray image. So pay attention to, I don't know if this should be blink. Yes, okay. So it's kind of, you can see that the rings increase in size a little bit, right? So let's do this again. Okay, so that's consistent with the prediction. The increase in ring angle is consistent. And we have XMM observations that are also consistent with that prediction. So it's not the first time this has been seen. There was a soft gamma ray repeater that was seen to do this in 2010. So here's an example of similar rings that were found around a transient X-ray source. So this was the first time this was seen on this scale with really clearly resolved rings that you can see increase in radius over time. Okay, so why do we see rings, and why do we see multiple rings, and why do they look like the way they do? So here's another cartoon. Any kind of echo, dust scattering or any other kind of echo, is produced on an ellipsoid. Right? Suppose you clap your hands. Right? I'm going to do that. Okay, so you're going to hear an echo. The echo is very short, right? So it's very hard to hear the echo, but there is an echo in this room. And it's probably mostly coming from this microphone. But so that's not included in the sketch, right? So So here's why it's an ellipsoid, right? You remember elementary school geometry. How do you make an ellipse, right? You put two pins and a piece of paper and a piece of string between them, and then you draw a circle, and that makes an ellipse. An ellipse is characterized by the fact that the length of these two arms of that triangle is constant for an ellipse, right? So the length to go from here to here and from here to here is the same as if you took this pencil and put it in a different position, stretching out the string. So an ellipse is a shape where the distance of any point on the surface to the two focal points, the sum of that distance is constant. Right? And so that means that the delay time of the photons or the sound waves that they take, rather than going directly from one focal point to the other, from the object to the observer, but by actually being scattered somewhere, that delay time is constant on the ellipsoid. And so if you wait a day, then the ellipsoid will be described by a delay time where the length of this triangle is longer than that by 1 day. Right? 1 light day or 1 sound day. Okay, so here are the different paths that the scattered signal can take, and they all have the same delay time because they lie on this ellipse in 2D, and in 3D that's just an ellipsoid. Right? So all the scattered signals at a given time delay must come from this ellipsoid. And why do we get rings? Well, there isn't dust everywhere. Dust is located in clouds, right? So we have concentrated dust in specific locations in the Milky Way. So let's put a dust cloud, and because this is a stretched cartoon, right, the dust cloud is actually very, very small. And this ellipsoid is really very, very elongated compared to the cartoon here. But we can only see, at a given time delay, we can only see scattered X-rays from the intersection of this dust cloud with that ellipsoid. Right? And at a later time delay, the ellipsoid will grow because the delay time is longer, and that means that the length of this triangle must be larger. And so this intersection must become larger and larger with time. Now we have multiple clouds. Right? We don't just have one dust cloud. And so each cloud has an intersection with that ellipsoid, and each cloud will make a ring. Now if you look at the Earth, right, and this is our neutron star, each ring will be at a different angle seen in the sky. The ring that is closest is going to be largest in angle. Right? So this is our echo from the closest ring. Now, from the closest dust cloud, it makes the largest ring. Right? If you just follow the echo for each of these clouds, you get a cone, and the opening angle of the cone is smaller the further away the cloud is. So that's why we see multiple rings, and this is really not coming out at all. I apologize for that. So this is our cartoon. We have 4 clouds, and here's Chandra. Here's our neutron star, and each cloud makes a separate set of rings. Now, multiple clouds give us multiple rings, but why the ring's broad? That's because the light curve of the flare is extended. Right? And so if there were a single flare, there would be a single time delay. But we get X-ray emission. This is the maxi light curve. We get X-ray emission from all these different points, and each has a different time delay. And that makes the ring broad, and that's why we see what we see. Okay, so here's the radial profile, intensity profile of the Chandra image. And you see the rings very clearly separated in the intensity. Right? So this is the innermost ring, the second ring, the third ring, and there's a fourth ring that we see in the image. And the question is, what can we learn from that? Right? So here is, let's see. Here's the light curve of the flare that produced the echo. And we know what the intensity should be given a dust scattering cross-section and a dust column density for a given cloud. We know how bright the echo should be as a function of time delay. And so we can turn this light curve into a dust scattering kernel. Basically, the first part of the light curve will be at the largest angle because it is the largest time delay. Right? And the last end of the light curve will be the smallest angle, and it'll be over here. And so if you just took a single thin cloud of dust, a sheet of dust between us and the source, and you calculated the dust scattering echo from that single sheet of dust, this would be the signal. So you can then deconvolve this intensity profile with that signal and pull out the distribution of dust along the line of sight. So let's do that. And here's the deconvolution you get. You get 4 clouds, 4 rings. Right? And so they're nicely separated in distance between us and the source, except this is not distance, this is angle on the sky. And the reason we don't know the distance yet, we'll get to in just a second, is that there is an ambiguity in the equation for the distance to the source and the distance to the cloud. So all we know right now is that there are 4 clouds that are producing rings at different angles on the image. So what is the distance scale, which we would like to put up here on the top axis? So can we do bat astronomy? Can we do echolocation of objects using this method? So here is that equation again for the angle of the ring that we see on the sky as a function of the distance to the source and the relative distance to the dust. Okay, so x is that stretch here, x times d is that distance, and d is the distance to the source. And you notice that both x and d appear in this equation. So by itself, we cannot solve this equation for either of them. It's ambiguous. So we have to know either x or we have to know d to solve for the other. And how do we do that? Well, we don't know the distance to the source, right, accurately, so we can't do it that way, but maybe we can find the distance to the dust. So here is the rotation curve, the galactic rotation curve, in the direction of Circinus X-1. That's that white line, and then you see different radial velocities as a function of galactic position. All right, so the center of the galaxy is here, and so you notice that this line is within the tangent point, and that means the velocity is double valued. That's unfortunate because we can't just invert a velocity to get a unique answer for the distance. Nonetheless, a velocity will give us 2 distances. That's not too bad either, right? So two distances is better than an infinite number of distances, so we'll take that. So this is the rotation curve, and the question is, where can we find the dust? So here is a Chandra spectrum, or this is imaging spectroscopy of the Chandra observation in square tiles on the 6 chips. Thank you, Belinda, for letting us use 6 chips. 6 chips on the image, and this is the intensity, and this is the absorption column. Right? So we just fit this with power law, absorb power law. And so the intensity has very clear peaks in certain locations, here, 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 and here, for the different rings in different locations. And then there's a very large absorption column by some kind of cloud over here. Right? Okay, so here's our XMM observation of the same echo. I leave it up to you to figure out which one is more beautiful. I had never done diffuse X-ray analysis with XMM before, and I hope never to do it again. So you do see the rings, right? So this is the inner ring. This is the second ring, ring A, as we call it, ring B, and then ring C is hard to see here. This is the best XMM observation we had. The other 2, unfortunately, were so affected by flares that we could not use them. So we can use them to analyze the spectrum of the point source, but we can't do anything about the echo with them. But this one is good enough to do it, and so we can use that as well to study the echo. And so the question is, where is the dust, right? What's the x in that equation? Where's the dust? And so the dust is in clouds. Right? The concentrated dust must be in clouds. There's dust in between the clouds, but the really dense clouds that give us the rings, that's where the dust is. And how do we find the clouds? How do we find interstellar clouds? We look in CO. So it turns out that the MAPRA Galactic Plane CO survey have been mapping that region of the sky with pretty high angular resolution and depth and spectral resolution. And they had published a square degree data cube that was just 1 degree off to the side of Circinus X-1, conveniently. So, but they were really, really generous in giving us the data, unpublished data, to the cube that covered Circinus X-1. So we looked in that cube. And so what we want to do is we take our observation of the rings and we observe them virtually in the MAPRA data cube and see if we can find corresponding clouds. So here is the spectrum, if you take the whole thing, of the CO emission in that region. So there are 1, 2, 3, 4 clouds, and this is extended, and then there's this 4th one here, positive velocities, which must be very far away. Right, so this is something like 15 kiloparsecs. Okay. So there are a number of clouds that would be candidates for the location of the dust. Now, as I said, the sight line towards Circinus is actually within the tangent point, so it's double valued. And so a single CO emission feature could be multiple clouds at the same velocity but different distances. So that's an ambiguity we can't break just by looking at the CO. So let's take a look at the X-ray image here. And let's start with the innermost ring. Right? That's the innermost ring, ring A. It has a really bright feature that was also clearly visible in the Chandra intensity map. And next to it is a region of that ring that is not very bright. Right? So there must be an excess of dust here relative to the segment next to it. And if the column density of dust is related to the column density of CO, then we would expect there to be an excess of CO emission in that particular location as well. So here is the gray is the spectrum just of the green segment here, and the black is the different spectrum between the green and the black here. Right? So the black is the excess of CO emission in this particular segment over here relative to that segment. And there's really only one cloud that sits at that velocity. And here's an image of that cloud. So it's about minus 74 kilometers a second, right at the maximum that you would get from the rotation curve in that direction. And so there is a very clear feature in CO, a very dense cloud that has this elongated feature, so elongated structure here. And overlaid in blue are the peaks and the intensity of the three images that we have in the ring, in the innermost ring. The first Chandra observations and then the XMM observation. And the peak traces out the maximum in the CO emission perfectly. And that's really a fingerprint that you can use to identify the inner ring with that particular cloud over here. Okay? So now we can associate the inner ring with this cloud over here. Okay. We can do the same thing for the next ring. Right? So the next ring B has a bright feature here, and it is sort of dim over here. And we can do the different spectrum as well. And then there are two clouds that stand out. There's one at minus 80, or at minus 82 kilometers a second. That's actually beyond what the rotation curve would allow. But of course, clouds have a velocity dispersion relative to the rotation curve, and so that's consistent. And so here's an image of that cloud. So the green is that ring. That's where the ring is brightest, and that's where that cloud is brightest. So it's consistent with that cloud being associated with the secondmost ring. So if we just associate the inner two rings with those two clouds, we have two priors on the distribution of dust between us and the source that we can then use to constrain the distance. And we can go back and look at the third and fourth ring, which in XMM you cannot distinguish. And that ring is bright sort of, most of the image. And if you do a different spectrum, there isn't really anything that stands out. So you can't really constrain the location of the clouds that are responsible for the outer rings at all. So it could be this, or this. So we can't really constrain it. It's consistent with the yellow, so the ring 3 coming from this cloud over here, where the peak of the brightness is where this cloud is brightest, and then the outermost ring coming from this feature over here, which is brightest in this location, which is also where that ring is brightest. So it's consistent, but we can't constrain it. Okay, so we have the distribution of dust along the line of sight from our deconvolution. We just don't know the absolute distance to the dust. We know the relative distance. So we can slide this distribution up and down the distance curve. And we know the radial velocity distribution of the CO. And so we can take our dust clouds and project them onto this curve. And we can take our CO clouds and project them up and down this curve. We can just slide this distribution up and down and see where it matches best. Nothing matches perfectly. As I said, for example, this object over here never gets to be on this curve because it's more than 1 sigma away from the galactic rotation curve. But we know it must be there because it's in the direction of the source, so it cannot be inconsistent with galactic rotation. Okay, so then we take our distance to the dust, which we can calculate as a function of distance to the source, and calculate what the radial velocity is for that particular distance to the dust based on the galactic rotation curve and compare it to this distribution. All right, this is not visible at all. Great. Okay, so I'm going to skip through that. So we do this, and we have two priors that we can place on where the dust can be based on the fingerprinting that we did on which CO cloud should be responsible for the inner two rings. If we do that, and we just demand that the two other rings are not produced by the same dust cloud, which is a weak prior, then we get this distribution, this probability distribution of the distance to the source from that association of the CO with the dust. And that distance peaks at 9.4 kiloparsecs, plus or minus about a kiloparsec, 1 sigma error bars. So now we have a statistical kinematic distance measurement to the source from the association of dust clouds with CO clouds from the echo. So now we can put the distance scale back on the plot of where the dust is. So this cloud is roughly 8 kiloparsecs, 7, 5, 4. Okay, so that astronomy seems to work. Now, remember, there is this blue thing here which is a clear absorption signal on the echo. And this means that whatever is doing the absorbing has to be either in the foreground or it has to be within the dust that does the emission. And so if we look for another cloud that could be the culprit, okay, so before we do that, here's the Chandra image of the column density distribution again, right? So there's this cloud. Now you might think that the white contours are actually contours of this, but they're not. They're contours of this particular cloud over here at about minus 30 kilometers a second that really maps very nicely to the location of whatever's doing that absorption here. So we interpret that as a foreground cloud, which is too close to see in the Chandra image because remember, closer clouds make bigger rings. So it would be, it's a clear prediction for future echoes. If we want to test the association of different clouds with different dust rings, we can look for ringy. Okay, so here's my summary. Circinus X-1 is the youngest known X-ray binary, less than 5,000 years old. It's born with a really low field. It's consistent with the rapid orbital evolution of the binary, so we can watch live the coupling of accretion and orbital evolution in the source. And we've done echolocation with this object. It's the first accurate distance to the source. Hopefully, there will be other ways to do it. It's too far for VLBI parallax at this point, but you never say never. And hopefully, we'll get more observations of this in the future. Thank you.
Anyway, thank you, Sebastian. If somebody can push a button and turn the lights on, we can all...
Then you,
All right.
all right.
Everybody wake up.
Wake up. Yes.
Yeah.
So what's the peak isotropic luminosity then for this?
For that distance,
Yes.
it's above Eddington. It's like 1.5 Eddington. And for the flare, that was not steady, right? So I think that was about 4 crabs, so that's like several Eddington. So, but that was a very short flare.
Yeah. Never?
Can you estimate the amount of flux which gets onto the clouds?
Yeah, so that's
Fraction of luminosity which was scattered and somehow drew the distance.
so.
It's possible, but
We wouldn't have to know the absolute fluence of the source to get the distance from that, which we don't, because we'd have to know that, not just the fluence, but the actual luminosity of the source, which depends on the distance, right? Again, you can't solve that independently.
I think this is like additional.
So there's a ratio of the flux from the source and the flux, or the intensity of the echo, but the distance cancels out from that ratio, so you can't solve it for the distance.
I have a question. Your explanation, because the ring you see are such perfect circles, your explanation requires the dust has to be a plate perpendicular to the slant side.
Not really, yeah.
Second thing is, if the cloud is continuous, you should not see distinct rings.
So there's a condition there, right? And so the condition is that in order to see a ring, the spatial extent of the cloud has to be small compared to the distance between us and the source. If it's not, then yes, you're right. You get a diffuse, halo, even if in response to a short echo. But if the size of the cloud is very small compared to the distance between us and the source, and we have every reason to expect that it is, because the distance is 10 kiloparsecs and clouds are tens of parsecs maybe, so it's a factor of 1,000 smaller. Then actually you expect a pretty well localized echo, and it doesn't have to be a sheet. It just has to be the relative size of the cloud has to be short or small compared to the distance in order for it to make a ring. And so even if the cloud is not perfectly planar, or it just has to be the size, the extent of the cloud has to be small.
We're back here, Josh.
So how well known is the binary period? This is really a strange system. This began by saying, you said 16.5.
16.5. Yeah, so it's evolving, right? And so, and it actually,
The next question, how well can it be? It's not measured very well. How well is it being measured to evolve?
yes, so that's a good question too. And it's, it's not measured from optical measurements, and there are 2 estimates, and actually I should have put them both up. So there's a radio estimate from, radio flares, and there's an estimate from the dips in the X-rays. And so there's a, very long history of the light curve with ASM and MAXI. And And the evolution in the X-rays from the dip timing, as far as I understand, gives you, that's the 3,000-year estimate. Recent radio measurements give you a longer evolution time scale, but that is not clear exactly what you measure in the radio, because they measure the timing of flares, and exactly when the flare happens in response to where the orbit is not exactly clear to me. So,
If it really is 16 days, this is not an LMXB.
right.
It must be an HMXB.
Yes.
And flare then is not any normal outburst.
Right.
It must be a gross,
There's something drastic happening.
outflow variation in a high-mass companion.
Yes.
superconductor.
Yeah. There must be some.
Was the spectrum very soft during that peak?
So MAXI does not give you a soft spectrum, right? It cuts off at 2 keV, so we don't know. I wish we had. I mean, it's also highly absorbed, so yeah.
Randall question?
But going back to this question of uniformity, if you had a bright enough source, couldn't you tell angular variations?
Yes, right? Which is in part what we do, right? So we see there are bright spots in the different clouds, and we associate those with bright spots in the CO. Yeah, so you do see angular variations. So I should point out that this isn't necessarily obvious, maybe, but we do see them, and this is in part what we use to do the identifications. And it's it's nice that you can actually find something that corresponds. So.
Let's go back. Jonathan?
Yeah, you say you give a limit of 4,600 years for the age. I think at some point in the talk you were giving a best guess of 2,600.
Right. So the best fit is between 2,000 and 3,000, but it's really not well constrained.
10 magnitudes of visual extinction.
Could you have seen?
600 BC.
Yes. So if we precess back the location of Circinus X-1, could you have seen it from Beijing, right? Or
ancient Greece.
Or ancient Greece. So
Too far south for Beijing,
it's-
not for Cairo.
yeah. So it's probably too far south. It probably would not have been visible, right? It's probably too extincted. Yeah. And it would not have been visible from Beijing. At 2,600 years, the Chinese would have had records of it, right? If it were visible. I don't know if we have accurate enough records from the ancient Egyptians to see whether there was a supernova in Circinus at the time.
Not reliably to rule it out, but,
Yeah.
but it might be worth looking.
I'll brush up my hieroglyph reading and go to work on that.
Are you going to be able to remove the rings to look for extended emission from the radio lobe?
I wish. So there's some work to do, yes. So I've looked. That would take some ingenious analysis. Maybe you can come up with it. I don't know. No, I don't know. We really looked hard, and it would be nice to say something about it. It's clearly not as bright. You see, even in the X-ray image of the nebula, right? So this is. I wish you could see it. So this is the Chandra press office's image of the remnant, right? So there's a clear brightness depression in the southern part of this nebula, even above where the chip cuts off. So it's less bright in the south. And you can try to explain that maybe by the explosion going into two-phase medium where the lower part of the image goes into lower density and it expands more rapidly, but then the density is too low to see it. We've done some initial 2D simulations that at least gives you the right shape, but it's too early for me to say anything about that more than that. So we hope to look again, and if the source stays dim, then Belinda will be hearing from me.
So the really interesting thing, of course, is do you learn anything about the interstellar clouds, CO clouds? Like you might get a dust to CO ratio.
So yes, so we try to do that. In this case, we try to estimate the amount of dust by the brightness in the CO, and it's consistent with sort of standard measurements of cross sections and dust to gas ratios. There are better objects to do this with, which I'm not showing you today, but you'll have to invite me back, or maybe somebody else, maybe Leah or Randall can tell you about that.
Yeah, so one more question or comment. So do you see the X-ray jets in this system? Because you were
Yes.
seeing jets, but
Right.
it wasn't clear that it's
Yeah.
visible. We just see
Here.
these lobes, but there's
Well, yeah, okay, so yes, so let's. Some people would call this lobes, we call it a shock, right? Yeah, so we don't see a jet, at least not clearly. And the jet and the radio, so this is an interesting system. I didn't say this, but in the radio it's interesting because there were claims, they're still around, that the jet and the radio has a gamma of 16 Lorentz factor. That would be huge for a galactic X-ray binary. And that would make it a really extreme object. The jets are seen on sub-arc-second scales. We do see extended emission. You cannot see it in this image, but there are blobs there. They're not moving, so we don't really see them moving. And so they're probably maybe background sources. I mean, they're both in radio and X-rays, but they're not moving. So either there's another stationary shock, right, like knot A in M87, or your, I don't know, 3C273, your favorite jet source that has a knot somewhere. But it's kind of weird that it's not moving on binary timescales in such a small system, right? So it would have to move.
Well, but can you look for the variations in the intensity instead of moving?
Yeah, we could do that. We haven't done that. Yeah. I mean, yeah. There's not very clear, good evidence that the X-ray jet is there. Mm-hmm. And the gamma of 16 claim, which would be really interesting, especially now that we have a distance actually a little larger, there is an ambiguity there because it's not actually observed proper motion. So, yeah, I'm not going to stress that too much.
So I thought that the scattering cross sections went to 0 around the element ledges. Is that true? And if so, can you look at this in different bands and get some information about the elemental composition?
So I don't know if we have enough signal to actually do that with this particular response. So you probably have to look closer in where the signal is brighter. Out here, the angles are quite large, so the cross sections are quite low. So it's not a very bright signal, right? We're pulling it out from above the background, but I don't think we have enough photons to do that.
Okay.
No more questions. Let's thank Sebastian again. Thank you for a delightful talk.
Thanks.
That was wonderful. And a variation on the theme.
Is it still on?
Do I introduce myself? Yeah.